Now we have then two voltage sources, E1 and E2, our three resistors. And so, like the previous examples, we want to assume that the current in this branch goes this way. So I1, because this source is positive on the top, we assume that the current goes that way. So I2. And likewise then, if we call this junction right here our junction A, we'll assume that I1 and I2 meets there and it goes down through here. So that gives us I3. Now, the end of the resistor where the current enters should be positive, and so the polarity for I3, likewise then, if I1 enters R1 on the left, positive on the left, negative on the right. If I2 goes through here, from right to left, positive on the right, negative on the left. Okay, so we call this one here loop 1. We call this one here loop 2. Write KVL around the loop. Start right here. Go in the direction of assumed current. Include in KVL a term for each component. So, for loop 1 then, we have plus E1, which is 10 volts. Then we come to R1 and we're going clockwise, so we're going from a positive to a negative. So that's subtract V1, and remember we want to write that in terms of Ohm's law, whereby it is equal to the resistance times the current, so 470 times I1. Okay, so the next component is R3. We're going down again. It's a positive to a negative, so a drop in potential. So that becomes subtract, let's put I1 there, subtract 220 multiplied by I3, and that completes our loop. So that sum is equal to 0. Now, we want to do some simplification on that if we can. And so we'll simplify to 470 times I1 plus 220 times I3. And so that becomes equal to 10 volts, or just 10. And that is equation 1. Now, I can solve that right now for I1 in terms of I3 if I want. But before we do that, let's go ahead now and write KVL for loop 2. And so I have, if I start here in the lower left hand corner, I can go clockwise, right? However, generally we want to go in the direction of assumed current for this. Okay, so let's start here, and we're going around and we're going up. So it's plus E2, and that's counterclockwise because of the direction of current. And the reality of it is, I don't really want to call that E2 because I should really write in the value of E2 instead. And so let's say that it is plus 5 volts. Okay, so now I'm going to go around in the direction of assumed current. So I got R2 next. I'm going from a positive to a negative, so that's a drop in potential. And 820 times I2. And now I'm going down here for the center branch, and so it's negative VR3, or subtract 220 times I3, and that completes our loop, so that sum is equal to 0. And likewise now, if I'm going to solve, I'm going to simplify this. I got 820, and I left out my subscript there again, I2, plus 220 times I3 is equal to 5. And now that becomes equation 2. And I have 3 unknown currents. So I need 3 equations. And so the other equation got to come from Kirchhoff's current law. So Kirchhoff's current law then at node or junction A. And again, the sum of the currents that enter is I1 plus I2. And that equals the sum of the currents that leave, which is just I3. And so to put all my variables on the left side of the equation, then I should say that I1 plus I2 subtract I3 is equal to 0. And that becomes equation 3. So I got 3 equations and 3 unknowns. And again, we can solve those using any method. And so substitution says that when we got this one here, right, with our 3 variables in it, and so this loop equation doesn't have an I2, and this loop equation doesn't have an I1. And so solve equation 1 for I1, solve equation 2 for I2, substitute them into equation 3, come up with a value for I3. Back to equation 1 with a value for I3 and come up with a value for I1. Go back to equation 2 with a value for I3 and come up with a value for I2. And then you arrive at a solution. Now, if you got a calculator with matrix capabilities, this is what you should do. Realize that now the matrix of coefficients is 470, 200. Oh, wait, no. And so you'll notice I didn't put in my I2. And I got to be careful about that because I need 3 variables. And so my second coefficient here is a 0 I2 and a 220 times I3. My second equation has a 0 I1, 820 I2, and 220 I3. My third equation has 1 I1, 1 I2, and negative 1 I3. And I want to multiply that by my first equation, the constant is a 10. My second equation, the constant is a 5. And my third equation, the constant is 0. And remember, it is the inverse of that, and that equals the answer. So we put this in your calculator, and you push the equal sign, and you come up with I1 at 13.9. I mean, actually what you get is 0.0139 because I1 is in milliamps. So 13.9 milliamps. Then you'll come up with I2 at 1.87 milliamps if I keep 3 significant digits for these. And you come up with I3 at, if I round it, 15.8 milliamps. And so your substitution will yield a very similar or really an identical result. So what that means now is I1 equals 13.9 milliamps. I2 equals 1.87 milliamps, and I3 equals, again, the sum of these, which 15.8 milliamps. And to verify that, that sum that comes in to be correct, put your numbers in this equation 3 here, and that works out pretty close. It might be a rounding error. You can go back now and check these two loop equations as well, because of course these currents here should satisfy equations 1, 2, and 3, of course. And so, of course, there's a small mistake here. We have shown the inverse of the matrix of constants, but of course that's an error. And we should have the inverse of the matrix of coefficients right here. And so it's a 3 by 3 matrix, and the inverse of that is also a 3 by 3 matrix. And if we multiply that by a 3 by 1 matrix, then you'll find that that gives us a 3 by 1 matrix. And the inverse, of course, of the matrix of constants here would be a 1 by 3 matrix, and we can't multiply a 3 by 3 matrix by a 1 by 3 matrix, because the way this works is this 3 cancels with this 3, and we're left with a 3 by 1 matrix. So please note that it is the inverse. When you put this in your calculator, it is the inverse of the matrix of coefficients here that you got to use. And so we have the enter the matrix of the coefficients, take its inverse, multiply that by the matrix of the constants, and the result then is the matrix of the variables. And we have, again, I1 at 13.9 milliamps, I2 at 1.87 milliamps, I3 at 15.8 milliamps. And of course that satisfies each of our equations 1, 2, and 3 if you check the numbers. Thank you. Right.